part of this, we are going to actually run statistical analysis using the GLM that we produced in the previous video. So for this, I'm going to first open up a new browser window just to see what FSL has about the VBM analysis. So I can do a Google search for FSL VBM, and we can click on the link. And this explains a little bit about the VBM, what it is. It has a very simple method description of it down here at the bottom of the screen that could go in a paper if you used it with the references below it. Of course, you can look at those papers. There's a lot more that you can go to, a lot of other references you can look at to read, to understand how you could write it up if you're interested in using this tool. I'm going to click on this user guide link. So for this, you really have 5 steps. First step, and they're all listed up here, first step is preparing your T1 images in the right format. That typically means having them named correctly in a directory and having them converted to Nifty file and everything like that. And so this would be an example here, preparing your data for the study. And in this example, you make a directory, you put in, so if you have 2 groups, in this case a control and a patient group, you put them all in order. Control typically are going first, and the patient group is going second. If you just have one group, they all go together in order with the ID or some sort of way to ID them. And then on the side would be the basic T1. And we can walk through it. For our purposes, we won't worry about that. This has already been done. But just to show you what one will look like. This isn't the data we're using for the class. But here's an example. So I have, these are T1 controls are all first, and the patients are all second. And this is a group of 40 different individuals. And so once that is created in some folder, with the T1 Nifty, D1 scans converted to Nifties, with the naming convention, then you're ready to start processing. So we could walk through the guide. We're not going to walk through the guide in this case, but you can go through this. We've already done this. The first step, then once it's all organized, is you run the brain extraction, and you can get into the different options for this. If your images don't have a lot of neck, you can probably run this first step, FSL VBM, with a -B. If the scans have a lot of neck, then you might want to add the -N instead. And it'll take longer to run, but it'll clean up the neck area. And then the next step is it'll create a template from your subjects. And so that is essentially an average brain from your group. You can do it from a subgroup if you want, but it depends on the size. If you have, say, 100 people, 100 scans in your study, you might not need to do it on everyone. You could do subgroups, but you'd want to make sure you have balanced numbers from, if you have a patient group and a control group, just make sure that they're balanced. And so in this other example, we're not using for the class, but in this example, I have 20 controls, 20 patients, and so we could use that for the creating the template. So after you scroll strip, then you run this command. That would be in the command line. So that would look like this. And we'll pretend this is the right location. But then you would just type in FSL VBM2 template -A or -N, and A uses an affine registration, 12 degrees of freedom. And so that's just sort of a rough registration to a common space template. Or you can do nonlinear registration, which you probably don't have to do that. That'll take longer. If you want a really robust template, then do the -n. But again, that can take significantly longer. But you would just type it in with whatever option when you're in the VBM directory, push enter, return, and it'll run. It'll take a little while to run. Once that's done, then you run FSL VBM3 proc. And that'll produce the images. It concatenates, so it stacks all the images together in alphabetical order. So that's going to be this order that they would sort. Again, that's really important that you know the order and have them in a logical order. And it'll stick them all together and that'll be almost ready to run the stats on. And you can check the image. So you'll always want to look at the image. And we won't do this for our purposes. I won't demonstrate it, but you can follow this guide. And then what we want to do is just statistical testing. We're going to use the tool called Randomise. FSL also has a newer tool that they're developing, have been developing. You could use that one is called Calm. But for this assignment and exercise, we're going to use Randomise. And so what you do, then you can run smoothing. So VBM, it'll smooth out the brain. And right here, it'll do a range. That's the same in this proc step. It'll do a 2 millimeter, 3 millimeter, 4 millimeter smoothing. And that'll just get rid of some of the noise, some of the variability that's caused either by noise in the scan or imperfect registrations, the brains to one another, the brains to the template really is what they're being registered to. And you can create other smoothing if you want. And that's what this is saying. You can take this merged file and smooth it if you want a different one than the 2, 3, and 4 that are spit out. Your smoothing, it would depend on what other groups have done. So if you were wanting to replicate findings of another group and they had done, say, a 3.5 millimeter smoothing, then you need to create that separately. If you don't want a different one, this will create the 2, 3, and 4 automatically. And what those look like is they're going to be in here. And so we have the GM, gray matter. This is a modulated file, but we don't worry about what that means right now. And it has this merged and S2, 3, and 4. So those are the smoothing 2 millimeters, 3 millimeters, and 4 millimeters. Often a 3 millimeters is a good one to look at. But again, there could be reasons for using the other ones. And that would come from a discussion with an expert, an imaging expert, or through reading the research on the groups that have used VBM. And then after that, we will run a tool called Randomise. So in the previous video, we created a design matrix and the contrast file. We're going to we'll look at those. And then this is showing an example of how you could run it. This is using different ways of thresholding the results. Typically, the recommended one is this called TFCE, threshold-free cluster enhancement, is typically what we want to run. So this is going to be our command here. And we'll get into that in a little bit. So the first thing we want to do is we need to create a script that we're going to run this on Hypergator. So to verify what we have, we uploaded in your folder. So UFRC, CLP 7934, share, homeless data, and then your folder, and then the CVK VBM class. Within the stats folder, we should have these files that are uploaded. The GM mod merge S3 in particular is what we're going to use. And then in the previous video, using the GLM tool, we created this contrast file, and here's the matrix file. And those are going to be the ones that we're going to use for this. So the first thing we want to do, though, is create a script. So I'm going to use Visual Studio Code here locally on my computer. You can use a different text editor. You can use Atom. You could use something on Hypergator if you didn't want to install anything. If you couldn't install anything, for example, if we went here, I'll reload this, ood.rc.ufl.edu. If you go to Interactive Apps, there's this VS Code. And so you could use Visual Studio Code on Hypergator, and that would start a GUI session, and you could do the code that way. But I'm going to do it locally. So the first thing I do when I open this application is we'll get this welcome screen. Or if you have already opened this and you've unchecked show welcome screen, welcome page on startup, then you might not see that. I'm going to start a new file and close the welcome screen tab. You don't have to do that. But now this is blank. So this is a new text file, this is our script. There's nothing there. So how do we know what to put in there if we're going from scratch? Back in the browser, I'm going to open a new tab or a new window and type in help.rc.ufl.edu and go to that website. So this is specific to research computing. And if we look over here, batch system, there's this annotated job script walkthrough or sample SLURM script. Either of those could work. Let's click on the annotated one just to show what you need. So you can walk through and say you need this at the top, common argument, and walk your way down and through the different options that you would need. Well, if we come over here to the sample, here we can see basic single-threaded job, multi-threaded. We don't worry about that. And so then, or here's an example at the bottom, all different examples you can use, probably including a GPU job. We don't need any of that. So what we're going to do is I'm going to copy this basic single-threaded job. And I will copy all the way down to the first commands, present working directory, host name, and date. So I copy those, and I'll come pasting into my script. And this is where we need to start editing. So now I'm going to call this a VBM randomise. With my initials, again, this is just a naming convention that's temporary, that's on Hypergator. You can call it whatever you want. And then mail type, end, and fail. Options are none, begin, and fail all. And so in this case, I'm going to keep these defaults, end and fail. A lot of people like begin in there as well. If you want begin and fail, then that would be all. But I just like end or fail. I know when it starts after I submit it. So then I'm going to change my email, but you can put in whatever you want. So I'm going to put my email in there. And then number of tasks 1 is good. Job memory request. This is where we need to request how much RAM. In this case, I'm not sure how much this takes. And so I'm going to request 6 gigabytes. It probably won't use that much, but we're going to use that much. And then time, the default here in this example was 5 minutes. We're going to need more time than that. This can take hours to run. So I'm going to change this to 24 hours. It shouldn't take that long. I'm going to change that to 24 hours. And then output, let's change the name, VBM, randomise, and then initials. But again, you can put whatever you want there. That'll be the log file that's written. And this will print, it'll keep a record of the current working directory, the host name, and date. And the host name is important, and the date can be important in case there were any issues. If there was an error and you didn't know why there was an error, you tried running this again, you could get an error, or you got an error on a particular process. It could be that the server has gone bad, and so it's keeping a record of it. And so then what we need to do is make FSL available. So we will module load FSL. In our case, we'll make sure it's the newest version of FSL. And so that'll be FSL/6.0.1. And let me make this a little larger on the screen if I can. There we go. Make it a little larger. Module load FSL 6.0.1. And then first thing I like to do is change into the directory that I need to be in. So CD, and then you can type in the path, but I'm also going to get the path from here. So if you don't have the File Explorer open, you can go log into ood.rc.ufl.edu, the on-demand file, then open the class folder, and then navigate to where this is. So I'm going to copy this path as a shortcut, and then I can paste that in there. And so now I know I'm in the right location. And then this is where we need to get the command to run. So the command to run, assuming we have all of these inputs, is going to be something like this. So I will copy this command and paste it in there. So what we need to be careful about is making sure that all of this is accurate. So our input, this is called GM mod merge S3. Now the problem with that is I changed, right now we have CD into this folder. Remember, you'd want to get the path that's going to be specific for you. But this is CPK VBM class. So let's look and see what's in that directory. Right now, it's just VBM data, CSV VBM data class. There is no GM mod merge S3. So what that means is this command won't work because this file is not in this directory. So where is that file? That is in a subfolder called stats, GM mod merge S3. So what we need is stats on the end of that. And of course, you can navigate to that location directly and copy the path. But again, we want to make sure that we're in the right location. Or we could specify the path here. We could put in all the whole path, et cetera, to that. But we're just going to run this from that directory. So that's our input image. And again, this is 3mm smoothing. And then this is a mask file that will run the stats, make sure that we run the stats just within gray matter. So this is a gray matter mask. We want to make sure that that file exists, as it does, gmmask.nii.gz. If we notice, I haven't specified .nii.gz. We can but we don't have to because FSL assumes that. If you don't put a file extension, it will assume it's either a .nifty or a .nifty.gz. And so you can leave it off, or we can put the file extension on. And then here is the output, and this is saying FSL VBM. You could leave it at that. You could be a little more descriptive, meaning in our case, this is a group of control, PD, so we can say control, PD, VBM, or we could just leave it as FSL VBM. Either one's fine. I tend to like to be descriptive. So I'm going to call it control, PD, VBM, even though it's a little longer. And now -D is our design matrix. And so this is where we need to get the name. So in this case, when I created it, I called it, so here's our .mat, this is our matrix. I called it con PD with age covariate. So I'm going to get that name from there. So within this tool, the hypergator, on hypergator, I can do rename move. I can copy that name and then paste it in there, or you can just type it. Again, I can move this over, and then here's our contrast. So I could type this in. I could type in con, PD, age, code. But we want to make sure that it's accurate. A small typo could cause this not to work. And so again, typically, I like to get the name from here. So I'm copying that. And just to be safe, pasting that over. And then this -T is the option to use threshold-free cluster enhancement. So that's the type of statistical correction that it does. And so we're going to leave that. And then N is 5,000. We don't need to get into that. Those are iterations, those are permutations. But it does make sure that the data are accurate. And if you click on this link, you'll see randomized usage, or you could do a Google search for FSL Randomise. And notice that this is British spelling, so with an S instead of a Z. Then you can get through the user guide. It talks about how you do the testing and how things are run. You could go through the theory. It gets very complex. And so this is this N of 5,000 these are Monte Carlo permutation tests. And so 5,000 is the default. If you really want to be a little more robust, then it'll take longer to run, but you would do 10,000. So for a class, you could do 500 or 5,000 for this assignment. But typically, you don't want to do, on anything that you would publish, you don't want to do less than 5,000. And I would recommend you do 10,000 on anything that you want to publish. But most people will just go with the default of 5,000. So that's the command to do the statistical test. And then that'll run. This will take a while to run, take some hours. And then usually what we do at the end of the script is just type date. And so this should be good to run. So a basic script. This is randomized, reloaded FSL. We're in the directory that has this concatenated, this file that has all of the brain images stacked together. So in this case, this is 80 different people. The first 40 are controls, the second 40 are Parkinson's patients. And then gray matter mass, so we look just within the gray matter and do the rest of the testing. So now we can save this. So I'm just going to save this locally. I'm going to put it in my downloads just to make it easy for me to get to it. And I'm going to call this my FSL VBM Randomise. I'll put my initials on it. Again, you can call it whatever you want. And then I'm going to save that. So this is local on my computer. So now I need to upload that. So I'm going to go back over to the File Explorer, and I will upload it just to keep it a little more organized. If you want to be really organized, you could do something like, I could have like a script directory, but I'm just going to put it in here. So however you want to organize this. Now I can upload, and upload this from where I saved it, in my case, download. And so now I can view it just to make sure it looks good. It looks good. And I'm going to verify that I have all the files. I have the matrix and the contrast. Ignore the other files for now. And so then that should be ready to go. And so then I can go to Open in Terminal and type S-batch. And if you don't remember the name of your script, you can hit Tab twice if you're in that directory. And so there it is, FSL VBM, and hit Tab to complete. And I will submit it. And now we're going to wait a little bit to see what happens, to see if it's going to run, if there's going to be errors. So one thing you can do, if you want to check, you should go back to Dashboard, and come over to Jobs, and then Active Jobs. And you can look at your jobs, and it should default to that. And so it shows that this has been running for 24 seconds. And I'm going to click again, going for 37 seconds. And if it hasn't crashed yet, it's usually a good sign. I'm going to go into that folder. I don't see that it's created anything yet. So I don't know if it is running anything. Because it hasn't created anything, but there is the log file. So if we wanted to look at the log file, again, I can go to File Explorer, and I can view the log. As we can see, it has starting permutation. It's already done 100. And now it's done more. So it needs to do 5,000, but that's one direction. Because remember, in the contrast on the GLM in the other video, we had done one test that said control higher than PD, and then another contrast of PD higher than control. And we can see that in stats, let's say in our contrast. So if I view this first one is control higher than PD. And then so control 1, PD negative 1. And then this one is going to be PD higher than control. And so it's PD with a 1 and the control with a negative 1. And the third column was age. And so a 0 in that column means that we are controlling for age in this analysis. And then these other ones were looking at just age relationships. So one has a positive relationship between the gray matter density and age, and the negative one would be a negative relationship between, so that's a correlation. You're testing if there's a negative correlation or a positive correlation, and a positive correlation. You're testing both between age and the gray matter. So what this is going to do, if we look at the updated log file. Now it's done more permutations, and so this will run, and it has to do 5,000 permutations for each test. If you did 10,000 permutations, it would do all of them. I mean, it would do 10,000 for each test, so it'll take a while to run. It's pretty fast, but it's not instantaneous. And so that'll run. Well, I guess I have a typo on my output. I was just checking, saying that doesn't matter. But that was right here. I had an extra O in there in my script. Again, that doesn't matter. This is a log file, but if I had done the typo down here in the command, then this wouldn't work. The script would crash. So I wanted to be careful and double check your script. So this is running, and that should be it. That should be good. And then once it's done, we can check the results, and I can do another video for that.